Hello everybody, welcome to lab today. Today it's climate, and climate is the average weather characteristics over a given region in terms of tens or hundreds, usually thousands and even millions of years. Climate that we know from the climate studies we've done, we know that climate changes throughout the past. It has been warmer and cooler in the past, and we know that climate changes. It's just one of the parts of climate. So climate does change. We know that right now we are currently in a warming period, and we would expect the globe to be warm right now and global warming to take place. There was a time about during the last 100,000 years when the globe has gone through global cooling events to the point where glaciers got so big and so vast that they covered much of the northern parts of our northern hemisphere, all the way down through Illinois. Many techniques are used to determine what the climate of the past was like. Of course, climate is very difficult to predict using computer models because there are so many variations and so many variables that go into calculating climate and climate change. It's really difficult to use computer models to go very far into the past or very far into the future about what climate was like. We can, of course, use some fundamental pieces of evidence, such as the rocks. The rocks, remember, are deposited in certain environments, and the fossils that live in them tell us a lot about the environments. But there are other techniques, things like ice cores, where a hollow drill core is drilled into the ground, and the resulting column that is pulled up out of the ice gives us layer upon layer of frozen air bubbles. So the ice cores have records that go all the way back tens of thousands, even hundreds of thousands of years, where we have samples or air bubbles that tell us things like carbon dioxide and methane content. We can look at the oxygen levels, and the oxygen isotopes tell us what the temperature was like. They even take these hollow drill cores and drill them into the ocean sediments, and they get readouts from the organism shells of carbon and oxygen ratios, therefore giving us temperature. So these things are paired together to give us a look at what climate was like hundreds of thousands, even some millions of years old. The more recent climate can be, we can get some more additional information. Things like tree rings, the cave deposits, mammoth tusks, lake deposits, things that give year by year growth can actually tell us a lot about what the climate was like as well. Different techniques are used for that. Specifically, we can actually use some of the lake sediments and bog sediments to get a sense of what sorts of plant life was present at the time. And plant life usually gives off pollen, which spreads all over the region. And a lot of the lakes and bog sediments have this pollen settle. And again, lakes and bogs produce new layers seasonally, and so we can actually go back and count the layers back and get good records of the types of plants via their pollen all the way back to tens of thousands of years ago. So pollen is widely used for paleoclimatology, which is the study of old climates. Today, we're going to zoom in and focus on ice data from Vostok, Greenland, and we will also look at a study done in Colorado for pollen and how the climate can be traced for each of those situations back. So dig in, climate starts right now. All right, everyone. In part one, we're going to be looking at the climate data that we can get from ice cores. Ice core data given every year can give us an indication of what the climate was like tens or even hundreds of thousands of years ago and further. And we can get ideas of what the carbon dioxide content was like, methane, and then even temperature markers. So some things to look at when dealing with this. And I'm going to go ahead and take you through a little presentation to explain how exactly this works. So this graph is the graph we're working with in part one. It is from ice cores from Greenland. And what they did was they took samples of the atmospheric carbon dioxide and the oxygen isotope ratios to give temperature and overlaid them on the same maps or graphs so that we can actually get a better look at them. A couple of things to note here. First of all, The first thing we actually notice from this graph, if you look at this graph close enough, that temperature rises first and then carbon dioxide follows. And if you look really closely, you'll see temperature rise first and temperature fall first and carbon dioxide follow. So the first thing we note then is that carbon dioxide and temperature are directly related to one another. And that's really the answer to number one. And number two, the answer then would be temperature leads carbon dioxide. What causes this? Well, actually, as temperature increases, the uh, level of carbon dioxide in the atmosphere increases because when the oceans heat up and when ocean water warms, it actually releases carbon dioxide into the atmosphere. When the ocean water cools, it actually absorbs carbon dioxide. And this has been responsible probably for the runaway greenhouse effect on Venus and the runaway refrigerator effect on Mars. Turns out that Earth is, of course, right in between them in the so-called Goldilocks zone around our sun, which is a very just right area. Now, um, why is it significant that carbon dioxide is rising and falling? Well, carbon dioxide is actually a greenhouse gas, and greenhouse gases are gases that absorb heat and therefore warm the planet. CO2 is not the only greenhouse gas. Methane is a powerful greenhouse gas, and so too is water vapor. Greenhouse gases are actually necessary to keep the atmospheric temperature stable on our planet, and they're necessary for life on Earth as we know it. If we didn't have greenhouse gases, the temperature would be well below zero all the time. So this is a good thing. So greenhouse gas isn't really a bad word. It is of note that carbon dioxide is about 0.04% in our atmosphere by volume. Um, the most abundant greenhouse gas is water vapor, anywhere from 0 to 4% in the atmosphere based on the water cycle. But the water vapor does absorb heat and thus is a greenhouse gas. So it's thought that as carbon dioxide increases in our atmosphere, it does help to heat the temperatures. And when there's more heat, more water vapor enters the atmosphere. Water vapor absorbs heat. So there's a little bit of a feedback loop there. But as you can see, these are very small amounts in our atmosphere compared to our nitrogen and oxygen. You compare us to our neighbors, Mars and Venus, who have a 96% carbon dioxide by volume in their atmosphere. It's pretty remarkable. One of the big differences about Earth is that there's life on Earth. And the life on Earth, specifically the little ocean organisms, they use calcium and carbonate in the water to build their shells. And so a lot of the carbon dioxide that may have been in the atmosphere today is locked up in the rocks thanks to life on Earth. Very interesting. Back to our graph here. Um, It is of note then that the temperature rises at some points and falls at other points. And it's likely, if we're going to look at number three in our questions, that when the temperature rises, that we are in a so-called interglacial period. And when the temperature falls, we are in a glacial period. And that's when the temperature um, goes so low that ice actually begins to creep onto the land surface and be tied up on land. Why does the temperature, and what we see from this graph here is that temperature and carbon dioxide have fluctuated over time. They've been high and they've been low. What is causing the temperature to rise and fall then? If it's leading carbon dioxide, what's going on? Well, first off, notice the top part of this graph here, it shows orbital shape, less elliptical and more elliptical. Back in the 1970s and 80s, studies were done to find and discover that the Earth actually goes through orbital cycles. These are called Milankovitch cycles after a meteorologist who studied this. And, sorry, he's actually a mathematician, Milutin Milankovitch. But at any rate, he noted that the Earth goes through cycles where its orbit gets more or less elliptical. That's called eccentricity. The tilt of the Earth changes, obliquity, and the Earth wobbles on its axis, precession. These things go through cycles at 26,000, 41,000, and 100,000 years, and they sometimes cancel each other out. Other times they line up to help each other um, amplify either in the cold direction or the warm direction on Earth. More solar radiation on Earth gives a warm direction, and less solar radiation hitting the Earth's surface cooler. The sun also goes through maxima and minima. The sun has cycles as well, giving off more solar radiation, which is received by the Earth's surface, or less over time. Here's a map of the sun's maxima and minima as you look back in the last 500 years or so. Today, we are in a modern warming period. We would expect the sun to be more active, and it is. There was a period back in the 1600s where it's called the Maunder Minimum. It's also known as the Little Ice Age. And it's thought that the Earth was going to go back into an ice age at that point because there is such low temperatures. Volcanic activity is thought to be a part of this. Uh, and also the sun cycles are thought to be. But the Earth's orbital cycles and the sun drive temperature. And as if you look back on the last, say, 10,000 years of Earth history, there's a little ice age there. There's been warming and cooling periods cyclically throughout. Noting that at the beginning of the Holocene, which is kind of our modern era here, that our modern epoch, that the temperature was warmer than it is today. And then you get to that last glacial period as you get beyond 10,000 years ago. So back to our graph, that is actually reflected in this. You can see that there are parts that are warmer than today, and then you go back and then there's that deep drop in the temperature back from the last glacial period. So question number 4 asks, has the Earth seen fluctuations of temperature in the past? And obviously the answer is yes. And has the Earth been warmer today? Yes, it has. 125,000 years ago, 325,000 years ago, based on this data. Actually, if you look back at this data, the last million years or so, the Earth has fluctuated greatly in its temperature. If you go back to 5 million years ago, look at the graph, you can see that the Earth has actually been warmer, much warmer than it even is today, or even in the warm period. And if you go back 65 million years, this is the last graph we looked at was right about here, from here to here. If you trace the temperature markers back in the late Cretaceous and early Tertiary periods, the temperature was 10 degrees plus C warmer than it is today. Really, at that time in Earth history, the oceans were just water. There was no ice on Earth, and the oceans were so high that much of the central part of the U.S. was covered in, or the southern part of the U.S., I should say, Georgia, Alabama, they were underwater. Illinois had oceanfront property at that point. So temperature has been warmer in the past, and temperature fluctuates throughout time. We go back to our graph, and it says, based on this data, make a prediction where you think CO2 and temperature are headed in the next 1,000 years. And based on this data, you might say that the temperature is likely going to drop, but that's uncertain. And unfortunately, it's uncertain because there's a unnatural, I can say, spike in the CO2 levels. And recent times we've seen this spike because of, and it's likely because of humans burning fossil fuels for energy, causing an anthropogenic rise in CO2, anthropogenic human cause. CO2 concentration in the atmosphere has been increasing unusually since the mid 1800s, particularly since the Industrial Revolution. And most of that CO2 is energy related burning, about 80% of it. And we also look at the last 100 years of temperature, noting that it is rising more than usual. This is the last 1,000 years. Of course, remember, we had the mini ice age there, and temperature was cooler, so we'd expect to see more warm temperatures today, but nonetheless, it is rising. And when temperature rises, sea levels rise, environments change for organisms, and sometimes this, especially if our CO2 levels increase too quickly, this warming could cause problems for species on Earth that are already under pressure because of human activity. So there are many effects of global warming, but if the global warming is too rapid, many ecosystems are threatened and pressured in an unusual way. So these are considerations. Really, folks, I think the bottom line here with these studies is that climate changes, that temperature does lead CO2 up and down throughout history, and it's likely going to continue to do that. It does that because the Earth goes through orbital cycles and the sun goes through cycles. The globe has been much warmer in the past than it is today. But human activity has really caused an increase in CO2, which is likely going to cause a warming that's faster than the Earth is used to. So environments are under pressure. Take home message: it's always really important to live synergistically with your environment, uh, so that you can kind of preserve the natural flow of things and we don't really get ourselves in the way. We haven't really learned much or done much to do that in the past. And humans really didn't think about climate change when they were building close to the ocean or in precarious land areas. But we need to get smart about how we are living with our environment, because it does help moving forward, both in taking care of our environment and taking care of us as humans. So ends part one, our discussion on ice cores, what we can learn from them, and what we have learned from them over time with climate and how climate changes. The next part of our lab, we're going to focus in specifically on the last 10,000 years, and we're going to look at how pollen data can inform us on how climate has changed. It's very interesting, so let's begin part two. In part one of the lab today, we've gathered sediments from a bog. And of course, I don't have the actual bog sediments from our study in Colorado on this pollen data. So I went ahead and gathered up 6 different kinds of sediment to use today for our bog sediment that represents 6 different layers in the bog. And in each of the layers of the bog, different pollen grains can be found. And again, in the interest of not of kind of avoiding learning about the different types of pollen and that sort of botany class, I've made the pollen grains today slips of paper. And the little slips of paper here represent the pollen grains found in the sediment sample. As well, I've labeled each of the sediment samples with where in the bog it would be found, the number 1 being the topmost layer, for example, the present back to about 150 years before present. This would be the first layer where we would find plant matter giving off their pollen and getting caught in this layer of bog. And again, the rest of the samples represent different layers in the bog. The next layer down in the bog would represent the pollen grains found in the sediment of that layer for about 150 years to 650 years ago. And the third layer, 650 years ago to about 1,500 years ago. And the next layer, 1,500 years ago to about 300 or 3,500 years ago. And then layer 5, 3,500 years ago to 8,000 years ago, and 8,000 years ago to 10,000 years ago for the sediment sample 6. But each of these bog samples has representative pollen that's going to tell us about the climate. The idea is to identify the pollen, identify the types of plants that are in the area, and then by that, noting that different types of plants like different types of weather and climate. Some plants like more moist environments, some more dry, some more cold environments, and some more warm environments. And so by looking at the types of pollen and a percentage of pollen in it, we can get a better sense of what plants were alive and therefore what the environment was like. And this is going to help us trace climate back about 10,000 years in this particular study. So your job is going to be your job was to eventually to come and piece out and pick out all the different grains of pollen and then arrange them so that they're in the different types and then count the different types. You're going to record the numbers of pollen grains for each type on your data table in your lab. And then you're going to calculate by adding all the pollen grains up and divided by the total number for each one. You're going to determine what percentage of each type of pollen is in each of the sediment samples. And that's going to give you then, okay, the types of plants in this particular sediment sample like cold weather and dry conditions. So you're going to be able to say that the climate is cold and dry. So that's kind of the take-home message here. What I'm going to do is go through and show you what each results were. I saved you the time of picking out all the pollen grains here. So I'm going to go through and show you the results of the pollen and what that information you're going to be able to fill in the table, the data table on what types of pollen you have, and therefore what types of plants you have, and therefore what type of climate you have. And then you're going to use that information to answer the questions. All right, so here we are with part one, looking at the data for the first sediment sample. And in the first sediment sample, we see having fished out the pollen grains. This sample is from 150 years to the present. And you can see that our pollen grains here, there are 7A, there are 8B, there are 5C, and 2L. And so I went ahead and made a big Post-it note there with them on, but I also included it in the table. There were 7 A's, which are ponderosa pine, 8 B's, which are meadowgrass and wildflowers, 5 C's, which are aspen, and 2 L's, which are alpine sage. Further, I went through and I added all of these up and got the total to be 22, and then what I did was I took 7 divided by 22, and then I multiply that by 100 to get my percentage, which is 32%. So my A's 7 divided by 2, 22 times 100. B, to get the percentage, I do 8 divided by 22 times 100. C would be 5 divided by 22, and then get the answer, and then take that times 100 to get the percentage. And then I rounded them as well. So my overall data then turned out to be 32% A, 36% B, 23% C, and 9% L. The rest of them I leave blank because there were no other pollen grains from any of those samples. Finally, I go on to my data key and I look at the codes and the plant species, and I get a sense of the climate characteristics of each. First of all, you can see that ponderosa pine, which is the A, are long needled pines that occupy warm, dry slopes, so it's warm and dry. B is meadowgrass and wildflowers growing in warm temperatures and summer drought, so again, warm and dry. And then C, aspens can live in wetlands but cannot survive in deep snow, so they definitely need it warm, and a lot of snow means dry, not very much snow means dry. So all these are warm and dry. So when I go to my climate and I put temperature, I'm going to go ahead and put warm because the majority of these said warm and the majority said dry. Now I will note that alpine sage here, L, there is 2 of those, low growing shrub that's found only at high altitude and cold sites. Judging by the others, this bog is probably in a low altitude environment where we got mostly this, but we could probably say that there was some high altitude areas where alpine sage was growing because we saw some pollen from there. It doesn't mean the predominant climate was cold because those only grow in the high altitudes. It just means that we probably had a warm, dry, low area and a highland that was growing some alpine sage. So that's an analysis of what the climate would have been like in this time. So once you do this for all the rest of the layers 2 through 6, you're going to find the numbers of pollen grains, calculate their percentage, and then look up in the data key to find the climate characteristics and list the climate as warm, cool for the temperature, or dry, moist for the humidity. Finally, you're going to come down and answer these analysis questions. So let me give you a look at the data for each of the layers. Okay, so here's my data for layer 1. Layer 2, layer 3, layer 4, layer 5, and layer 6. Now that you have the data for all of our layers, go on through and write in the numbers of pollen grains, then go calculate the percentage of pollen grains, then determine your climate characteristics, temperature and moisture, and finally analyze the climate in the resulting questions. I hope you enjoyed our lab on climate. I hope you're able to get some take-home messages such as climate changes, the globe warms, the globe cools. We can actually get a good sense of how the climate looked in the past, and the climate has been warm and cold, warm and cold. In fact, the climate has been much warmer than it is today. We also looked at how the CO2 today is ramping up, and that has the potential to warm things up a little bit faster than we would like, and causes species not to be able to catch up, especially with all the pressures that human activity puts on our Earth. So with that in mind, it's always good to live it synergistically with our environment, to be smart about how we use our resources and use them wisely, use them effectively, and take care of our planet as well. So thanks for joining me for the Lab on Climate. I hope you have a great week. And again, please don't hesitate to ask any questions that you have.